This is Chapter 6, Gravitational Fields. This chapter is part of the field units, which focus on comparing and contrasting three fundamental fields in physics: gravitational, electric, and magnetic fields. After completing this chapter, you'll be able to describe key properties and characteristics of different types of fields, explain the specific properties of Earth's gravitational field, apply principles of circular motion and universal gravitation to solve problems, analyze planetary orbits and perform calculation involving orbiting, compare and contrast concept of the gravity in a Newtonian mechanics with understanding of the gravity in an Einstein general relativity, and describe the nature and significance of the black holes and dark matter in modern astrophysics. Section 6.1, Newtonian Gravitation. In this section, we will explore Newton's universal law of gravitation, including how the gravitational force is calculated and the concept related to it. We will examine how gravity acts between two objects and how its strength depends on mass and a distance between two centers, and how it governs the motion in a solar system and in entire universe. When we learn about circular motion in the chapter 3, we learn about center-seeking forces that are several known forces like gravity, magnetic force, normal force, or friction force. We call those centripetal force. So the centripetal force that keeps the planet moving in their orbit around sun is the same force that causes an apple to fall to the ground. This is the gravitational force. This universal gravitational force of attraction acts between two objects with mass, keeping the planet in motion around the sun just as it pulls the object toward its surface, or precisely toward center of the earth. This gravitational force is the responsible force that governs the universe. Another way of looking at the universal gravitational force is as an example of Newton's third law of motion, which says for every action force there will be a reaction force which is the same magnitude but the opposite direction. So that means if the object 1 is attracting the object 2, the object 2 is attracting object 1 with a force which is the same magnitude but opposite direction. So there's a pair of forces, action-reaction forces. One example is the Earth-Moon system. As a result of these forces, the Moon and Earth each orbit the center of mass, which is the center of gravity of the Moon-Earth system. Because the Earth has a greater mass, 6 times greater than mass of the Moon, this center of the mass lies within Earth itself, not far from the center of the Earth. So that means when we say that Moon is orbiting the Earth, we may not be as precise as it should be, because Moon is orbiting the center of gravity of that system itself. So Earth also, in addition of spinning around itself and orbiting the sun, is orbiting that imaginary center of the gravity between Earth and Moon system. So that's why the Moon is affecting the motion of the Earth around sun, and we see the Earth is wobbling. The better explanation for this would be if the mass of two objects are comparable. Like in the example that is in the diagram on the right, when we have two massive as a star, we call it binary stars, then the center of the gravity is going to be outside of each of those stars. And the more massive star is going to orbit closer to the center of the gravity, and a lighter star is going to move away, is going to orbit away from the center. What is gravitational force? Gravitational force is a mutual attraction that exists between two objects with mass. The strength of this force depends on the masses of the objects and the distance between them. It increases with a greater mass and decreases with a greater distance between them. So the formula is Fg is equal to a g m1 m2 over r squared when g is a constant of universal gravitational, which is 6.673 times 10 to the power of negative 11 Newton, times meter squared divided by kilogram square. And r is not a radius. R is a distance between centers of two masses. In the right side diagram, you're going to see many examples how the force will change as you are changing the masses or changing the distance between two centers of masses. The simple rule is more mass, more force. More distance, much less force. Let's see how a universal gravitational constant was determined. In 1798, the English scientist Henry Cavendish concluded an experiment to measure the very small gravitational attraction between lead spheres. From this precise measurement, he was able to determine the value of the gravitational constant, which he found to be 6.673 times 10 to the power of negative 11 Newton meter squared over kilogram squared. By knowing this constant and using Newton's law of universal gravitational formula, Cavendish was then able to calculate the mass of the Earth. His work was so accurate that it is often referred to as weighting the Earth. How was it done? Look at the diagram on the right, top right. There's a elastic rod there that is held in the ceiling where the mirror is glued, and at the bottom of that elastic there's a rigid rod which hold a pair of small masses. The light source is used as a point source to point toward a screen, and it will be useful to notice the change, the twist of that rod. Then he approached those two small masses with a two pair of big masses. As those masses approach each other, the force of attraction between pairs of two masses applied, which made that elastic rod to twist. As elastic rod twists, the mirror will change its position, twist as well, so it will reflect that point light in a direct location. By measuring that location and just keeping that notice there, Cavendish replaced the same twist with another elastic force, and measuring the elastic force and making that elastic force equal to a force of universal gravitation, he was able to determine value G. Universal gravitational force practice. Find the mass of the Earth using the G, universal gravitational acceleration, which we already use, which is 9.8 meters per second squared, and the radius of the Earth at a certain location. For example, in North America, which lies between equator and North Pole, the value of the gravitational acceleration is 9.8 meters per second squared, and the radius is roughly 6,370 kilometers. So given here is gravitational acceleration and radius. Find the mass is required. Formula itself is Fg is equal gm of the Earth, mass of any mass, any object, and r square is the distance between center of the Earth and that center of the object. But since the object is going to be small, that is like a center of the Earth. So we know that universal gravitational force is equal to the force of gravity at the surface of the Earth that we used to use all the time in the past. Okay, so by making those two forces equal to each other, because it's the same thing, we make formulas equal to each other. Gm of the Earth, mass of the object, over r squared is equal to mg. And as you see, m and m cancel, so you don't really need that mass of the object at all to determine the mass of the Earth. So solve for mass of the Earth, which is gr squared over g, capital G, universal gravitational constant. And then we plug numbers. For g is 9.8 meter per second squared. For r squared is 6.37 times 10 to the power of 6 meter, all in power of 2, divided by gravitational acceleration constant, which is 6.67 times 10 to the power of negative 11. Then you plug those in the calculator and you get 5.962 times 10 to the power of 24. Here is another practice. What is the universal gravitational force between two planets if their masses are 1.23 times 10 to the power of 26 kilogram and 5.21 times 10 to the power of 22 kilogram, and they are 230 million kilometers apart? So let's write what is given, what is required. So mass of the first planet, mass of the second planet, and the distance between them. Remember, the distance is million kilometers, not meters. So it's another 10 in the power of 3 there to convert kilometers into a meter. So it's going to be 2.3 times 10 in the power of 11 meter. So what is gravitational force, universal gravitational force? The formula itself is gm1 m2 over r squared. Then you can plug numbers which are already in standard units. And answer is 8.08 times 10 to the power of 15 Newton. And this is the force each planet exerts on each other. It doesn't matter each way or how fast the planets are moving, the force is acting toward each other that along the lines that join two centers. Universal gravitational force and tides. What are tides? Are the change in water level of oceans. The tides are a result from the difference between the gravitational force at the Earth's surface and at the Earth center. And that depends on lining up. If the moon, Earth, and sun are lining up, as you see on the diagram on the top, they are called spring tides when there are drastic changes. Spring tides are higher high and lower low tides than normal. When the position is perpendicular, so moon, Earth, and sun are forming a 90-degree or perpendicular to each other, then the tides that are formed are less drastic. So they are called neap tides that are lower high and the higher low tides than normal. So they are less drastic. Gravitational force and gravitational fields are related, are connected. Look at the gravitational force as we learn. It will depend on square of distance. If you look at the force and distance relationship in that graph is exponential. Gravitational force is inversely proportional to square of distance, and direction of the force is toward center of that mass. In this case, is center of the Earth. If you look at a diagram that shows the field vectors, and field is a vector quantity as well, those are directed toward center of that mass as well, which the field and force direction matches. A gravitational field line is a line that indicates the direction of the gravitational field that acts on a test mass placed on a field. The test mass is any mass that is very small, small enough that is not going to affect the gravitational field of the big mass by its own field, by its own gravity. The gravitational field lines is similar to electric field lines that we're going to learn in the next chapter, which point in a direction that is a positive test charge when a move in a place in an electric field. More about electric field and electric test charge we're going to learn in the next chapter. Looking at the diagram on the right, we see the gravitational force and gravitational field vectors look alike. This diagram pretty much is very similar as a gravitational field as well, pointing toward the center of that massive body. In this case is Earth. Gravitational field is a collection of vectors, one at each point in space, that determines the magnitude and direction of the gravitational force, and the gravitational field strength is the magnitude of the gravitational field vector at the point in space. So it's very, very similar. How can we determine the magnitude of the gravitational field strength? We will do the same way by making universal gravitational force that we learn from Newtonian gravitation and the normal gravitational force formula that we learn from the second Newton law. By making those equal to each other, you see the masses will cancel and you find the formula of gravitational field strength as Gm over r squared. Gravitational field strength, G, is defined as a gravitational force per unit of mass. So that's what we do. We use the second Newton law, which is based on gravitational acceleration, or gravitational field strength is the same thing, is equal to force divided by mass. The force is a universal gravitational force. The formula, as we know, is G mm over r squared. In this case, we have mass of the Earth and a radius of the Earth divided by mass. So mass and mass cancel. G is Gm over r squared. In this way, by knowing the mass of the Earth, which is a constant, and the radius at the specific point in that location, we can look, for example, in North America, we can find that G is 9.8 meter per second squared. The importance of a universal gravitational force is because it's universal. It applies everywhere. To calculate the gravitational force acting on an object with mass m at a height h above the surface of the Earth, and the gravitational field strength at that level, we can use Newton's law of universal gravitation. So force is equal to Gm1m2 over r squared, and r is distance between center of the Earth and center of that object. So that means is radius of the Earth plus height of the object above surface of the Earth. So Gm of the mass of the satellite, for example, mass of the Earth over r of the Earth plus h, all in the power of 2. In a very similar way, if you just get rid of m, you can find gravitational field strength at that level where the satellite is. It is G_m over r Earth plus h in the power of 2. Let's compare and contrast gravitational mass and inertial mass. Gravitational mass and inertial mass are actually equivalent, the same symbol and same value. However, how do they refer to based on the concept that we cover? Inertial mass, as described by a second Newton law, measure the amount of matter in the object that determine how much it resists change in motion or acceleration when the force is applied. This is connected with a second Newton law formula: force is equal to mass times acceleration. On another side, gravitational mass from the law of universal gravitation measure the strength of the object gravitational attraction toward other masses. And the formula is force is G_m over r squared. In this table, you will see some useful data. In one column there, you see the value of the planet gravitational field strength relative to Earth and the absolute value of that same respective gravitational field strength in a Newton per kilogram. In the 2nd century AD, the Alexandrian astronomer Ptolemy proposed a model of the universe in which the Earth is stationary at the center and the Sun, Moon, and other planets revolve around it. Although this geocentric theory was ultimately incorrect, it was widely accepted and remaining the dominant view of cosmos for many centuries. In the early 1500s, the Polish astronomer Nicholas Copernicus challenged the long-standing geocentric model of Ptolemy, which placed the Earth at the center of the universe. Copernicus proposed a revolutionary heliocentric system in which the Sun occupies a center position and the planets, including Earth, revolve around it. He suggested that these planetary orbits were circular. He also introduced the idea that Earth rotates daily on its axis, which explained the apparent daily motion of Sun, Moon, and stars across the sky. In the late 1500s, Danish astronomer Tycho Brahe made the most precise observation of the planets and stars long before invention of the telescope. Brahe proposed a hybrid model of the universe, combining elements of Ptolemaic and Copernican system. In this model, planets revolve around the Sun, but the Sun in turn revolves around Earth, keeping the Earth in the center while partially acknowledging the motion of the planets around the Sun. The Italian scientist Galileo Galilei was one of few to support the Copernican heliocentric model. He improved the telescope and used it to make groundbreaking observations: 4 moons of the Jupiter, craters of the Moon, and phases of Venus. These discoveries shows that not everything revolves around the Earth and provides strong evidence for the Sun-centered solar system. The German astronomer Johannes Kepler, a contemporary of Galileo and assistant of Tycho Brahe, shared Galileo's beliefs in the Copernicus heliocentric model, which placed the Sun in the center of the solar system. By carefully analyzing Brahe's precise observation of the planetary motion, Kepler discovered that planets do not move in a perfect circles as previously thought, but instead follows elliptical orbit around the Sun. This is an amazing video. I highly recommend. The link is going to be below. Enjoy. And finally, we reach the end of this lesson. Here's a summary. The universal law of attraction states that the force of gravitational attraction between any two objects is directly proportional to the product of the masses of the objects and inversely proportional to the square of the distance between their centers. So force of gravitational is gm1 m2 over r squared. The gravitational constant, capital G, which is 6.673 times 10 to the power of negative 11 Newton meter square over kilogram square, was first determined experimentally by Henry Cavendish in 1798. The gravitational field can be represented by a vector at each point in space, pointing toward the center of that mass. Gravitational field strength at the distance r from the body of the mass m equal to the magnitude of gravitational acceleration at that distance. G is gm over r squared. Please do your homework.